All right, guys, we'll go ahead and get started. So last week's exam is fully graded, just may not be input into D2L yet. Dr. Zalecki and I both finished grading our parts, and we've sent that spreadsheet over to the LA who inputs those into D2L for us. So you should probably see those today, I would assume. If she doesn't get to it today, then tomorrow. Homework 2 or homework 5 or 6, I believe, was due this morning, and you'll get those grades back before next week's recitation. During first recitation, I made a note. So today's recitation is going to be it's going to be on the shorter side. We'll probably finish about 10 or so minutes early. And the reason for that is since it's the first week after a recent exam, there really hasn't been a lot of material introduced. So today, for the majority of time, we will talk about differentials and linear approximations. With that being said, I did want to make a note about taking y double prime with implicit differentiation. Implicit differentiation isn't new, but finding y double prime is. I've gotten a few emails from students asking for clarification, and Dr. Zalecki didn't give me any problems to go over today as far as y double prime and implicit differentiation goes, but I did just want to touch on that really quickly. It's not even, I wouldn't say it's not worth putting up an example, but it's exactly the same as it would be if we just did regular implicit differentiation. So you're going to differentiate implicitly. You'll isolate all terms with a y prime to one side of the equal sign and all terms that do not have a y prime to the other side. Factor out so that you get y prime by itself. Then you've got your y prime equation, which is in terms of x's. And so you'll take the derivative of that again implicitly. So odds are you're going to have to do the quotient rule because it'll be a fraction. And then inside of that, you're going to have a y prime probably. And you can't give your y double prime in terms of y prime. So y double prime cannot be equal to an equation that has y primes and x's in it. And so the way to work around that is that you're just going to plug in the original y prime that you took. So that first equation or the first round of implicit differentiation, when you isolated that y prime and then took the variable or the derivative again, you'll take that y prime and just plug it in for any place that you see a y prime. And that's all I really had to say about that. Does anyone have any questions on the last exams material before we start trucking into the new unit? Okay, then we will get started. All right, so section 2.9, linear approximations and differentials. So as far as, there's really not a lot of concepts to unpack for the strategies that were, or not strategies, I'm not sure what the right word is, but these problems that we're going to do today, they build off of taking derivatives, which is what we just did for that entire past unit. There's really not a lot of higher level concepts that we're going to introduce today. These are just different applications of things that we've already learned. So linearization or linear approximations, it's kind of similar to when you would find the tangent line. If you look at the formula for, or the equation for a linear approximation, it has, this is going to be a constant, which is going to be synonymous to this b here. We've got our slope, which is our m. And then right here, we have a change in x, basically. So that's the main difference between these two. They're not exactly the same, but you can liken them in the same sense that they are approximation techniques. So when we think about what taking a tangent line is, say we've got a curve negative x squared, and we want to find what the approximate derivative is at this point 1, at x is equal to, or a equal to 1, the tangent line that we find is an approximation. This is similar to that. We will do, so this first example is just a simple linearization. It doesn't really ask you to, it's not a story problem or anything like that. We'll do one that has a more specific application. And that'll be kind of like the trademark problem that we do linearization for later on in recitation. But as far as this problem goes, it just is taking the derivative, finding that constant and plugging and chugging. The majority of today's recitation will just be plugging and chugging. You'll hear me repeat myself from time to time because there's not a lot of concepts to explain here. So if we're asked to find the linearization L of x of a function at a, given that a is equal to -2 and f of x is equal to x cubed minus x squared plus 3, we're going to use this equation. When you're asked to do linearization, you're going to use this equation pretty much every time. Not pretty much, you will use this equation every time. And so what we've got to find is this here and this here, because we already have a. So, excuse me. So we're just going to plug in our A for every point, determine the terms that we don't yet have an answer for. So we're going to take the derivative of f of x in order to find out what f prime of 2 is. This should be fairly straightforward at this point, considering we just took an entire exam on differentiation and story problems surrounding differentiation. So we're going to do the power rule, drop the 3, reduce to 2, and then power rule again. And so now we've got our general derivative, which we can plug in any x value to and get the specific derivative at that point. This is not an estimate or an estimation. This is an exact equation. It'll give you the exact derivative at whatever point you take it. And this is the estimation technique that we're being asked to demonstrate our understanding of, but still within it, we have this concrete derivative. And so when we plug those in, we get that the derivative is 16. And then so we also need to find what f of negative 2 is. When we plug into the original equation, we get that that constant is going to be negative 9. And so plugging that all into our linearization equation and then distributing out, oops, not distributing, but rearranging terms and consolidating, we get that L of x is equal to 16x plus 23. Any questions on how to do a simple linearization problem before I talk big picture? Can someone say something just so I'm sure that my audio is working again?
Yes.
Perfect, thank you. All right, so in terms of the big picture, well, I don't know if big picture is the right way to put it, but when you are given a problem like this, compared to one that we'll do later on, it is perfectly fine to give your answer in terms of x, because you aren't given any information that would allow you to plug in for that x yet. We'll see what that looks like later on. I did want to take an aside and just point out that leaving your answer with x's is sometimes the right way to do it if you aren't given the information to come up with a specific and numerical answer. But on the recent exam, there were a handful, I would say maybe close to 10 students who, and I know I had mentioned this in past recitation, so I just wanted to reiterate this, who would evaluate the derivative of a trig function, and they were given the instant at which you were asked to evaluate that trig function, and they would leave it in terms of x. I believe it was like sine of 2x, maybe 8 sine of 2x or something like that was a final answer that I saw pretty frequently. So what I'm trying to say here is if you're given the information to find the most specific answer, you should. When it comes to trig problems like that, you're going to lose points if you don't. When it comes to another example that we'll do later on, you will lose points if you don't. But for something like this, you aren't given any more information, and this is going to be your final step. And I'll come back to this idea of what is a good final answer and what isn't when we get to our next linearization example. But for now, we're going to move on to finding some differentials. We'll do about 4 of these examples. So a differential is just dy. We'll talk about the difference between delta y and dy in a later problem during this recitation, but delta y and dy are different. So defining what a differential is, the differential dy is defined in terms of dx by the equation, let me zoom out a little bit, by the equation dy equals f prime of dx. Now you can memorize this, but there's really not much to memorize because this isn't anything new to us. We know that the derivative f prime is the same as saying dy dx. If I ask you to take f prime of x, it's the same as me saying, hey, here's f of x, take dy dx, or here's y, take dy dx. And so you can think of it in terms of plugging into this equation when you do these problems, or you can think of it in terms of setting the derivative equal to dy dx, or just calling it what it is. And when I say the derivative, I mean the symbolic derivative that we'll come up with, and then cross multiplying that dx across. And so what dy is generally is an estimation of the change in y. And then we'll talk about delta, well, I guess I don't need to wait till later to say this, but delta y is the more specific change in y. Dy is an estimate of the change in y. So moving into this first problem, I haven't talked to Dr. Zalecki about this, and I can't say that I have specific evidence that you would lose points for not doing what I'm about to suggest that you do. But when I was taking AP exams in high school, when it came to calculus, the general rule of thumb was if you're going to use a function, the general rule of thumb was define your functions before you just start throwing symbolism out there. So if you're trying to find dy dx, label this maybe f of x, so that you have defined what the function is in terms of which variable. It's not hard to do so. And then you'll see also down here, we'll have an example with t. I think lower, we'll have an example with b. It's just, in my mind, it's just crossing your t, dotting your i's, and making sure that you are giving a perfectly accurate mathematical sentence. And so with the differential, all we're gonna do is find f prime. And we aren't given any information about what instant at which we're supposed to evaluate y prime. And so dy is just going to be equal to the derivative that we take times dx. So we'll take the derivative of f of x, f prime of x is just gonna be, so this is a chain rule problem. We'll start with the outermost aspect of the function. We'll drop the -2, reduce by 1, keep everything within the parentheses the same, and then multiply by the derivative of this inside term, which is going to be 2x. Now I do some manipulations here that aren't necessarily required. So I popped this, so instead of having it to the -3rd power, I popped it down to the denominator and have it to the +3rd power, which are equivalent statements. And as a conceptual reminder, I set it equal to dy dx. So now basically what we're gonna do is we're gonna cross multiply this dx across, and that is our final answer. Now, when we do some, so we've had problems throughout the semester where I've said, if this is all that's being asked of you, if all they want you to do is take the derivative, for example, then there's no need to really simplify. But if taking the derivative is an intermediate step to finding a later answer, then it's usually in your best interest to simplify. So this is not an intermediate step. This is simply find the differential, but we will do a problem here shortly after we get through these 4 differential examples that finding the differential is just one part of it. And so that's a case where you would want to simplify. Any questions on evaluating a differential before we move on to the next example? It's fine. I didn't imagine there to be a lot of questions today. Like I said, not a lot of concepts to unpack here. So let me know if I'm going too quickly, but at the same time, there's not really a lot to stop and explain. All right, so 11b, we've got y is equal to 1 minus t to the 4th. And what I've done is I've defined the function incorrectly. I believe I did that again. I used x later in this problem. And then I also put it into a fractional power form because I know that to find the differential, I'm going to have to take the derivative. And to take the derivative, I'm going to have to do the power rule. And so I'm going to have to know what power it's in. And so taking the derivative, we drop the 1/2, reduce by 1, and keep everything on the inside the same. Then multiply by the derivative of the inside. So I do another simplification, I believe. Oh wait, no, I do not. Oh yeah, I combine these 2 terms. And then I set it equal to dy dx. You don't have to do that. You're not going to lose points for not setting it equal to dy dx, but that is just how I conceptualize these, just because it feels like these problems are so bare bones that I feel the need to kind of throw in some more explanation. But you wouldn't lose points for not doing for not setting it equal to dy dx. And so then when we cross multiply or plug in, however you choose to think about it, we get that dy is equal to -2t cubed over the square root of 1 minus t to the 4th times dt. Okay. Next problem. So I probably should have been a little bit more explicit as to where the 1/2 power is being applied. I think that a lot of us would infer that 1/2 power, if you didn't see the tangent of square root t, say it wasn't presented to you that way, say that all you were asked to do is find the differential given y is equal to tangent of t to the 1/2. I just wanted to point out again that this is different from, say, if the 1/2 were right here, or say if we had parentheses and then the 1/2 were on the outside of the parentheses. So those last 2 that I just mentioned, if the power were right here, or there were parentheses and then the power were on the outside, then the entire tangent of t term would be to the 1/2 power. But in this case, this 1/2 power is just being applied to the t. And that's something we've talked about in the past. So we're gonna do this problem just like the other ones, plug and chug. We'll find the derivative. Derivative of tangent is gonna be secant, and we're gonna keep the constituent of the trig function the same. And then we'll take the derivative of the constituent and we will get 1/2 t to the -1/2. I did a simplification. You don't necessarily have to. And then cross multiplying, or however you wanna think about it, we get that dy is equal to the derivative times dt. Next example, we've got y is equal to 1 minus v squared plus 1, or over 1 plus v squared, which I have defined as f of v. So we'll take the derivative f prime of v, and it'll be a quotient rule problem. So we got the derivative of the first times the second minus the first times the derivative of the second over the second squared. Excuse me. So I simplified this just because, having looked at this positive 2v, negative 2v situation, I just imagined that it would shake out pretty simply. You don't have to simplify it at this point. But one thing I will say is that there's really no reason to expand this denominator here. We'll do problems later on in the semester, those big all-encompassing problems I keep alluding to, where we try to graph a complicated equation. And that's a time, those are problems sometimes where we will try to divide things out of the denominator, but there's no reason to do that in this case. And so it simplifies to be -4v over the bottom squared. And then, just like the other ones, we get that dy is equal to the derivative times dv. It is important to make sure that your variables match up. Like how I made this mistake up here, you would probably lose points on a free response problem. I would say a 0.5 point to a point if your variable does not, if your symbols don't match up. Any questions before we move on to a little bit more complicated ones?
If you can't like fully simplify the equation like you were doing in the more complicated ones, how do you set up the cross multiplication?
I'm not sure I understand your question fully, but let me try to answer it. And if I don't answer it correctly, we'll go from there. So the cross multiplying, that's not going to be, whether or not you're able to do that, that's not going to be contingent on how simplified your problem is. If the cross multiplying is kind of a roadblock in your head, you can just think, okay, I've got to find the derivative. Doesn't matter how complicated the derivative is. And then I'm going to plug it into this dy is equal to the derivative times dx dt, whatever the equation, whatever variable it's in terms of. For the problems that I was talking about where it's an intermediate step, again, you don't have to simplify those necessarily. The differential, like the derivative aspect of the differential, it just makes it easier for yourself. You'll probably have less mistakes. But at the same time, if you were to plug into an unsimplified derivative, you would still get the same answer. You just have to plug in more x or t or whatever values. So what I was talking about earlier about being able to, okay, so this next problem that we're about to do, for this first one here, we can't put in x. That's what I was saying, how this isn't an intermediate step for this particular problem, because this is all the problem is asking us to do, and this is all the context we're given. But all of this we're gonna do for this problem here, but then we also are able to plug in x. So we'll get a more simplified answer. So I think that I've been talking a lot about what is a satisfactory simplified answer and in different ways. So does that serve to clarify the different things I've been talking about in terms of simplified answers?
Yeah, thank you so much.
Yeah, no problem. Okay, so compute delta y and dy. So like I said, delta y is going to be the exact rate of, or the exact change in y. And we're going to think about delta y. So we're all familiar with this equation, change in y over change in x. This is the slope equation. And we're going to disregard the denominator actually. But to find this, it's y2 minus y1. And then it would be over x2 minus x1. And the reason this is important, actually, I'll come back to this in just a second. But so like I said, we're going to compute both delta y and dy. These are going to be two independent aspects of this problem. They really aren't going to interact much. So one of these is not going to be an intermediate step for the other. It's just find delta y and then also find dy. And we're going to do that for the given values of x and dx is equal to delta y. We'll come back to this equation or this these two terms that are set equal here towards the end of the problem. But if you notice, dx is not noted here. And so for them to point that out, that means that we're probably going to have to take into account this property to finish this problem. So coming back to this delta y here, we don't really care too much about the delta x, just to kind of give you a frame of reference. But delta y is going to be the later y minus the earlier y. So the change in y is just going to be your new y minus your old y. And so when we're asked to compute delta y, we're going to have to find the new y minus the old y, the new function value minus the old function value. And we're going to have to do this in terms of the information that is given to us. So the old y is just going to be f of 3. But we know that over the scope of this problem, though that x is going to change by 0.5. It's going to increase by 0.5. And so we get that the new y is just f of the old x plus the change in x. So we get f of 3.5 for our y2, and we get f of 3 for our y1. So then we'll compute from this equation. We get these two values, and we get that our delta y is 1.25. Does this bit here make sense? I'll take the silence as a yes. Okay, I made a little note, new y minus old y. It's pretty much the same as this concept here. And then just plug and chug from there. So that's the end of finding delta y. Now we got to find dy. So dy is going to be done finding it's a differential, right? So you can think of plugging into this equation, or you can think of dy dx being equal to the f prime of x that you find, and then cross multiplying that dx across, however you want to conceptualize it. And so we'll find f prime of x, which is a simple power rule problem. And from there, we get that dy is equal to the derivative times dx. And the new step here is that we have the ability to plug in for dx, because we're told what delta x is, and we're told that delta x is equal to dx. So this first part of the problem, this delta y, obviously we didn't do that for this problem up here. But all of this, all these steps are exactly the same as everything here up until it comes to plugging in this delta x. We weren't able to, or plugging in x. Did I say that right? Not linearization. I was referring to one of these problems. My bad. But we weren't plugging in for delta x or for x. We weren't given the information to plug in for these differential problems. For this one, we have the ability to plug in for both x and delta x. We're given both of those pieces of information, and that's why for this problem, it's going to be different. You're going to want to come up with the most simplified version of the answer. We'll do some problems later on. Actually, I'll come to that. I'll bring up what I was about to say when we get to that problem. So any questions on this problem? We're going to do one more example, but basically the way these problems shake out is delta y and dy. The only difference in finding this differential is that we've got the information to be able to come up with the specific differential, because we're given information about the specific instance at which we're evaluating this differential. So one more time, if there are any questions, let me know. Otherwise, we'll move on. Fantastic. All right. So y equals the square root of x minus 2. We're given the same information. Well, we're given x and delta x. I just want to backtrack really quick and say, I wouldn't say that on an exam you would absolutely be given this property. You might have to remember and infer this if you were asked to find the most simplified version of the answer. So I would just kind of keep this in your back pocket. This is a review problem or a textbook problem, which we generally, our exam questions are somewhat similar to those, but at the same time, it's kind of like how I mentioned with the last exam. Sometimes he'll say use implicit differentiation. Sometimes you'll see a mixture of x's and y's, and you'll have to infer that you're supposed to use implicit differentiation. This is one of those things where he might put it in the question, or you might have to drudge it up from your memory. So we're going to go about this problem exactly the same way. We're going to find delta y. In this case, it's going to be So our y2 is going to be f of, and I didn't define this function as f. I should have. I didn't say y is equal to f of x is equal to x, or the square root of x minus 2. But I guess in this case, I did it in terms of delta y. Never mind. So for this problem, we're going to have 3.8 as our y2, or as the x input for our second function value. So, and that comes from 3 plus 0.8. So we got y2 minus y1. And then we refer to the original equation, y is equal to the square root of x minus 2. And this right here on an exam would be a perfectly acceptable answer. That is not correct. There we go, square root of 1.8. I don't know how to, I could come up with a decent estimate in my head, but I don't know how to take the square root of 1.8 personally, and Dr. Zielecki won't expect you to either. But I just threw up this answer anyways. But this is the answer that I would leave if it were a free response. So that's delta y. We'll move on to dy, or to finding the differential. And so we'll take the derivative. It's a chain rule with power rule. No, not chain rule. Sorry, it's just power rule. So we drop the 1/2 and reduce by 1. Keep everything on the inside the same. I guess you could say that it's a chain rule because technically the derivative of 1 or of x is 1. And so you could say that we are multiplying by 1 over here. But anyways, moving on, we get that dy is equal to the derivative. You wouldn't be expected to do this fractional power manipulation necessarily. You can leave it in this form for all I care and just multiply by dx. But you will eventually have to do a fractional power manipulation for some of these problems. If, say, for example, the answer is, okay, let me start this over. So if it were a free response and you weren't asked to find the specific, say you weren't given the delta x or something like that, you were just finding a differential, say it was one of these problems, this would be an acceptable answer. Say, for example, you, so if you're gonna have to compute the final answer, it's going to be simpler for you, like I've mentioned before, to simplify it and then just go about it as a fraction rather than thinking in terms of fractional powers. So if this is an intermediate step and you need to find a final answer on a free response, it will be helpful to you to simplify it. Now, the last thing I want to say about this is, say, for example, you had a multiple choice problem and it was this exact problem on a multiple choice. You might have to come up with this 0.4. It's really not that difficult of a manipulation, but that's a situation where you might have to simplify in order to match your answer with theirs. Your answer wouldn't necessarily be wrong if you put it as this on a free response, but say you're trying to determine what the correct multiple choice answer is, you may have to simplify in that case. Because I have seen, I believe I've seen some free response problems like that. Okay, we're gonna move on to our last couple of problems here. And these will be, so like I mentioned for this first problem, this is going to be the classic, like the trademark problem that you'll see for linear approximations. And that's when you're asked to evaluate what a number or what a term is, whatever, this 1.999 to the fourth, or this down here that you just would not know how to do in your head with or without a calculator. And so we're going to use this linear approximation technique to come up with the most, or to come up with a relatively accurate estimate. So we're going to find the linearization of f of x, and we're going to call f of x equal to x to the fourth so that we can think of it in terms of 2, because we know how to find 2 to the fourth, but then we're eventually going to plug in our 1.999 to find the specific value that pertains to it. So we're going to use the 2 to set up our L of x equation, and then we'll plug in 1.999. And this f of x is equal to x to the fourth because we're going to regard this inside here as a variable. And then, so then it's x to the fourth. So I'll erase this bit down here. So we've got the linearization equation for reference. But for the linearization equation, we're going to need f of a and we're going to need f prime of a. We already have we already have what we need for this. And so we need to find these two. So f of 2 is equal to 16. And then f prime, we just drop the 4, reduce by 1. We're going to find f prime specifically at 2. I think this is 32. Yep. And so now we've got the information we need to plug in. And this is going to be our linearization equation that will be a general estimate for whatever value we want to plug in for x. And so we're going to plug in a 1.999. And so L of 1.999 is equal to 16 plus 32 times 1.999 minus 2. And so that shakes out to be this value here, which once distributed shakes out to be this. So again, if it were a free response problem and you didn't need to use this as an intermediate step or something like that, this would be a fine answer. I wouldn't expect you necessarily to waste your time coming up with this answer. Well, actually, I take that back. This is simple enough that I would expect you to come up with an answer like this. So for example, on the most recent exam, if it's a longer free response problem, then Dr. Zalecki will most likely give you credit for this because he'll be looking at your answers more in depth. If it's, say, like the first 10 questions of the last exam, that's credit, no credit. And so I would come up with this answer. I would give the most concise answer possible if you have all of the information necessary. Because like I said, it's credit, no credit. If it's the second half of the exam, which Dr. Zalecki grades, I would expect him to give you credit for this. So again, it just kind of depends on what problem, if it's multiple choice, if it's an intermediate step, whatever. Or you could just disregard all this mumbo jumbo and simplify every single time, and that'd be fine too. All right, so one more problem. Again, f of x, we're going to treat this as cube root of x, where a is equal to 1,000, which is roughly equal to 1,001. And so again, we're going to come up with f of 1,000 to set up for our linearization equation. We'll also come up with f prime of 1,000. So we know that the cube root of x is actually equal to x to the 1/3 power. So we'll drop that 1/3, reduce by 3/3 in the power up here and get negative 2/3. Plug in 1,000. And since this is an intermediate step to coming up with a later answer, let's talk a little bit about this fractional power manipulation, because I know that a decent amount of students struggle with coming up with these sometimes. And so we just plugged in our 1,000. Now we got to deal with this negative 2/3. So first thing to do is to get rid of this negative and put it in the denominator. I think we're all comfortable with that at this point. The big thing to point out is that when so now we've got two aspects of this power to crunch through. The big thing to point out is that you always want to get smaller, not bigger. So we're going to start with the denominator because that's the cube root part. It's basically saying we're going to cube root it and we're going to square it. So let's cube root it first so that it's easier to it's going to be a lot harder to cube root something that's already been squared than to square something that's already been cubed. It's always easier to go smaller before bigger. And so the cube root of 1,000 is 10. And then when we square that, we get 100. And so our final answer is 1/300th. Then we're going to plug into our linearization equation all of these values we've just found. And so this, again, is our general equation that is going to help us to come up with this estimate here. This is a linearization equation. You can think of it kind of like a tangent line. It's not exactly the same, but it's an estimate nonetheless, or estimation technique nonetheless. And so we're just going to plug in our 1,001 for these x values. And what we end up getting, so this here is just going to be times 1. So it's 10 plus 1/300th. And I honestly disregard this. I don't think that it's not very common for Dr. Zalecki to expect decimal answers on exams. So again, I'll say that this will be an acceptable final answer. Any questions on the application of linearization to estimate these more complicated numbers? Okay. So we finished up about 14 minutes early.